Danger zone. Let that down. Yep. So, welcome, guys. Welcome, everyone. Hope you had a great holiday weekend. Sounds like a lot of you did. Um, Today is probably gonna hopefully be a little bit more chill. It's kind of a lot with the presentations and the exam and the homework assignment due and everything. So today I'll hopefully be a bit more chill. And I just kind of wanted to start by, taking a look at some of the logistics because we're halfway through. We're exactly halfway through the class. The good news is, as you're probably already mostly aware, the second half is basically just a copy of the first half. So we're going to be, the topics are different, of course, but the structure and schedules basically exactly the same as the first half class. So for the next couple of weeks, 2.5-ish or so weeks, I'll be presenting more topics, most of which are related to the remaining two homework assignments, although we have a couple of topics that are less, I guess, related to the final couple of homework assignments that are still important. Otherwise, I wouldn't talk about them. You do, of course, have one more presentation coming up, and I would encourage you to, start claiming dates. Some people have already started claiming dates and claiming papers. So, if there's a particular date that you would like to present on, please let me know. If there's a particular paper that you want, there's still, I think, more than enough on Canvas for you to pick from, although I think at least a couple people have started looking for other papers to present as well, which I think is fantastic. Just make sure you run it by me if you don't pick one that's on the pre-approved list, so that I can give it a thumbs up. But yeah, definitely get that scheduled. If you don't get it scheduled by next Monday or so, then I'm just going to start assigning people to dates again, which again is not a problem. Just trying to make sure that if you want input on when you present, you've got about a week to let me know when you want to present. If there's a particular paper that you want to present, you should definitely consider doing that sooner rather than later before somebody snatches the paper that you want. So, what else do I want to say? All of the first rounds of presentations have been graded. You should have got your feedback back on those. I was very impressed. Of course, there's room for improvement. There always is. I have room for improvement, right? I've been doing this for 15 years now. So always room for improvement. I hope you take that improvement as, positive feedback still, right? I'm not trying to hound anybody or make you feel bad. I was very impressed with the presentations. I know that some or maybe all of you were nervous, and that's totally understandable. I think that you all did very well. And, looking forward to see how the second round of presentations go. Spoiler alert, they almost always go better, even better than the first round does, because people are a little bit more comfortable, know what to expect a little bit more. Plus that feedback from me usually, hopefully helps a little bit. We've got 2 more homework assignments left to do. I checked before class and it looked like most of you had homework 2 due submitted to me already. If you don't, it's actually not, I'm not upset about that either. I told you last week that if you needed to take the weekend to submit homework 2, that I don't have a problem with that. So if you haven't got homework 2 in yet and you still need a little bit more time to submit it, that's fine with me. Although I definitely would prefer to see it submitted probably within the next day or two if you haven't done so already, because we got that homework assignment coming up next week, which is what we're going to be talking about, at least in part today, after we get through some of the other stuff. What else is there? The exams. I've started grading the exams, but as I believe I mentioned last week, we got a makeup exam that we have to take, which will happen this week. And as soon as that's done, I'll get that makeup exam graded and get those grades back to you as soon as I can. But I'm not going to obviously release the grades until after that happens. So still going to be at least a couple more days until you get those exam grades back. But I will make sure to get them back to you as soon as I possibly can. Probably on Thursday, if everything goes according to schedule. Because we're for Wednesday, right? Yeah, just make sure. Yeah. So probably on Thursday is when you'll get those exam grades back. Does anybody have any questions about? That's kind of a lot of stuff. Last week was busy, like I said. Does anybody have any questions about where we're at in the class, logistics, things like that. We've already gone through everything once before, so hopefully things are pretty um, understandable at this point in time. I wanted to take a moment actually before we hop into today's topic, which is one of my favorites. I love talking about OpenMP. I think the next two homework assignments, I really enjoy them. They're actually very real world practical problems. Not matrix multiplication isn't a practical problem, but we kind of beat that one to death, right? So we're going to take a look at some different kinds of problems. 3 and homework 4 that are a lot more able to be practically applied to real world situations. So I think you're really going to like that. But before we hop into all that stuff, I want to take a moment to kind of nerd out a little bit about the top 500 list that came out. It actually came out last week, but we were so busy with the presentation stuff that I didn't really feel like I had a ton of time to talk about the new top 500 list. But it did come out just last week. I would encourage you to take a look at it. You don't need to, of course, it probably won't be on the exam or anything like that, but I do think it's interesting to see what changes have been made. In fact, the biggest change, which is a little surprising, at least to me, is that there is a new number one supercomputer. There's a new fastest supercomputer in the world, and it's in China. So that was something that I kind of talked about when we talked about the top 500 way back in the beginning of the class. I don't think there were any computers from China in the top 10 at that moment in time, which I thought was a little bit unusual. And then, boom, they just came out swinging, right, with their brand new computer. It's called Line Shine. Has just been introduced and is now the fastest computer in the world. There are now, I believe, so this is the column, this is the actual measured column, the measured speed. So if you see any that are over 1,000, like this one is barely at 1,000, that's an exaflop. So they like saying that we're now in the exaflop. We've peaked over, 1,000. Well, we peaked over 1,000 petaflops into the exaflop scale. We now have 5 computers that can do an exaflop or more. The column that's next to that, this R peak, this is not actually a metric that has been hit. It's the theoretical max. It's on we have this many number of cores, and if we were able to operate all of these cores at 100% efficiency, then theoretically we could have this super duper high top speed. And so one thing that's really interesting to look at is how close these two numbers are, right? Because you can see here that while this one is technically over an exaflop, its theoretical maximum is almost twice as high. So it's really getting 50% efficiency on this particular benchmark. Let's be clear, this is only using one particular benchmark, that impact benchmark. Whereas some of the other computers on this list are a bit closer. You can see the one right below it is pretty close to its theoretical maximum. So, they're getting a lot of good performance out of it, even though it's not fastest. But the fact that China is back on the top of the list is, I think, the biggest news story here, and not terribly surprising. I didn't expect China to fade away from the supercomputing world entirely. In fact, I think I haven't had enough time to really dig into this to find out for certain, but I'm fairly sure that this computer actually existed before and has been up and running for a little while now. They just didn't actually submit it, want to publicize it so much, which is typically, it's not terribly unusual, right, for places to do things like that, especially when you consider that almost all of these, I believe all of these actually are in the top 5 are owned by governments. The American ones for sure are financed by the government. Question, yeah. What is achieving the right? Yeah, well, so the big thing there is, I'm sorry, what was it? Sure. There are lots of factors. I don't know that there's necessarily one thing that you could point to say for certain. One of the big things, so just to give an example, the reasons that I think are going to be different based on sheet. But to give an example, the top one they mentioned has, I think, very few accelerators on it, very few GPUs, very few things other than just CPUs on the machine. So of those 13,700,000 cores, they're almost all CPUs. Almost none of those are GPU cores. So that is, I think, an explanation as to why they're maybe not necessarily hitting their peak flops because if you have that GPU acceleration, that can help with certain kinds of applications. But that's not always the reason because a lot of these other ones do have GPU accelerators. So in that case, it might be the network that's holding them back or the power dissipation that's holding them back, right? They can't run their CPUs at full power because they would melt or something like that. So there's multiple reasons why. And the benchmark itself might also be part of the reason why. There are different benchmarks that exist. In fact, they're all here on the top 500 site. Um, so some of the other this is another major one. It's about graph computing. So this one does not use LinPack is based off of matrix multiplication. So it's linear equation solver is what the benchmark is basically. But this one does a different kind of computing. This one does, I'm not as clear on the specifics, but it does it based off of graph computing. So we're computing nodes and edges in a graph, which is structured very differently from, a two-dimensional system of linear equations. So we're really trying to flex a different set of muscles here for the computer. And so you can see that while the number one is actually the same on both lists, which is quite impressive for it to be the best at both. As you start going down the list, you can see that that's not always true. Here's our Fugaku, which we've talked about multiple times in this class, number 9 on the traditional list, but number 3 on the graph processing list, which might make a lot of sense when you consider their own custom interconnect that we sort of talked about, which might make those graph kinds of processing tasks a bit easier for that kind of computer. So lots of different reasons go into this. There's the top 500 list, while useful, is only one way of looking at it. It's the most popular way, right? It gets the most attention, gets the most news, and I don't see that changing anytime soon. But it's not the only way to evaluate these machines. In fact, there's a third benchmark, which I know they mention on this site, but I'm not sure they actually have the list on this site, which is a mixed precision benchmark. The idea there being that with the LINPACK benchmark, you're set to, I think, 64-bit floating point values. It might be 32, but I think it's 64. Regardless, the mixed precision allows you to fudge with those numbers a little bit and allow some of the computations to happen at a lower level of precision because that gets you a lot faster speed. That's actually a typical programming trick when you're using a lot of GPUs. So because GPUs are better at handling lower precision numbers because it's a lot of smaller cores as opposed to the bigger, beefier cores like CPU. So the mixed precision list will do better on machines that have lots of GPUs on them, as opposed to the traditional impact list will. So lots of different ways to kind of evaluate these machines. There isn't a single list that's going to, say which. I mean, they are trying to say which one is the best, but you always have to take that in context, right? And a different list may have a different gear at the top. While this is certainly the most common one that people refer to, and very impressive to see, it's important to understand that even for the kinds of problems that are being run on these machines, a lot of them probably are matrix related, but not a lot of real world problems don't fit inside of that. So they are using other programming paradigms, which aren't going to hit that same point. So it's just not. Yeah, great question though. There's a lot of countries on this. I focus mostly on the top 10. I mean, I know there's 500 on the list, but that's a lot to try and take in. But it's interesting to note that there's a lot of countries in the top 10 now. China is, of course, at the top. The U.S. is on there with the next 3. Then we've got Germany and Italy's on there twice. And there's Fugaku down at number 9 now. It used to be number 1. And Switzerland rounding out the top 10. So Europe, the United States, Japan, and China, those are usually the big players in the high performance computing scene. It was a little surprising that China wasn't where it is, but now kind of a return to form, and I expect them to continue doing that. As far as the computer itself, um, a lot of it's proprietary. This new computer, a lot of it is actual proprietary stuff. So the chips are specially designed chips for this machine. And I'm sure that they probably don't want us to know all the details about those chips, right? The operating system that's running on it is a proprietary operating system developed by the uh, People's Republic of China, right? That's the operating system it's running on, and they don't want us to necessarily know all the stuff that's so. You know, while there is information available about this machine, there's some stuff that's still kind of hidden behind the curtain, and that's true for the United States machine as well, right? I'm sure there's stuff that the U.S. government is holding in their back pocket too. They don't want anybody to know about. That's sort of the nature of the game. There is a hidden arms race going on here as well, or maybe not so hidden, right? It is kind of an arms race here with these machines, but a fascinating one to watch, and we get to see some of it play out in front of our eyes, which is really interesting. At least to me, it's very interesting. A lot of different architectures represented up here too, because you can see some of these are using AMD chips, some of these are using Xeons, which Prashant was presented about just last week. Some of them are using different kinds of chipsets. There's actually a yeah, here's one that's using Xeon with Microsoft Azure. So Microsoft has their own entry on the top 10, which they're trying, right? Microsoft's not typically known for excelling in this area, but they're trying. They're really trying to break in to this scene, and they have one on the top 10 now. So kind of interesting to watch and see how that goes as well. We already talked about how Gaku has their own custom chips too, that custom interconnect. They're tied closely to the Fujitsu company, which is a big hardware manufacturer from Japan. So lots of cool stuff. Yeah. How much value is there in it? I mean, it the peak value? Yeah. Well, the the question is, could they ever actually get there, and what would it take to get there? I think I'm not sure I can answer that question for El Capitan, right? The people who are engineers on that machine would have a better answer to that question than I would. Um, how much value do you think it has? I mean, it's a great question. I think the answer depends on everybody's interpretation. Yeah. Yes, in fact, I mean, this is kind of a sneak preview of a topic that I'm going to talk about a little bit later on, but there's a list called the Green 500, which breaks it down by gigaflops per watt. And so you can see that the number one machine on this list is number 445 on the top 500 list. So in terms of actual compute power, not that great, but in terms of efficiency, it's the king. So this is something that they're definitely paying attention to as well. And you have to scroll down. You know, you don't see any from the actual top 10 on the top 10 of the green list. I think if we can pull up the full list, we'll eventually see. Yeah, here's number 6 right here, HPC 7. So at number 11, and then I'm surprised that. There's the one from Germany. I thought the Fugaku was pretty high up on this list as well, but now I'm not seeing it. It was number 9. So the big machines are pretty high up on this list, but they're not, at the very tip top. And some of these machines, which we'll see next week when I talk about power consumption, that's one of the topics on the agenda for next week. Some of these machines get that by doing some non-traditional kinds of power consumption tricks, or the way that they deal with cooling and stuff like that. That's how they get those fancy numbers. So yeah, we'll talk about that next week. Great questions. Any other? I love talking about this list. Well, I probably shouldn't spend all of class time talking about this list. We do have to get to our topic. But if you have any other questions, I'm happy to indulge for at least a few more minutes longer. I think it's absolutely fascinating. One other thing you can do before I shut up and move on, there's a lot of different ways you can break down these lists. So the website's actually pretty good in terms of um, providing charts and graphs about these machines. They don't always have all of the information for the machines, but you can definitely break down the list in many different kinds of ways. So, uh, what was the one that I was going to look for? Processor. That's not really what I was looking at, but well, the countries one is always a fun one to look at. There's the US in green. Uh, Blue is, oh, that's others. It says Japan, then Germany, and then there's China, number four, France, South Korea. I kind of lump the European ones together. Maybe that's not fair to do, but a lot of times they are, the European countries are working closely together on this. Not all of this stuff. So yeah, if this is if this makes you nerd out as much as it makes me nerd out, you can go home and take a look at all these stats and really get a feel for what is actually on this list. It's really fun. I think you are allowed to just yeah. All right. I think that's enough of that for now. Let's switch over to the topic of the day, which is OpenMP. And this is one of my all-time favorite things to cover in this class, to be honest with you. Uh, whoops, I clicked the wrong button. Of course I did. Oh, come on. And we're going to be hopefully doing a little bit of coding today. Not a lot of coding today, but hopefully doing a little bit of coding today. Um, we're certainly, at the very least, going to be taking a look at some code examples today, even if we're not writing a whole lot of code ourselves. But I hope that we'll get a chance to make some small tweaks to the code as well and do a little bit of exploration in advance of the upcoming homework assignment. So let's go ahead and get into it. OpenMP has been around for quite a while, especially when you consider how fast things move in the computing world, right? It's been around since the late 90s, and you can see all the companies that were involved. This is back in the late 90s, all the companies that were involved in first creating this programming framework. All the big names on there. Cray exists as a brand, but I believe they got bought out by Hewlett Packard. I could be wrong about that. But all of the other companies that you see on that list very much still exist today, very much still big players in the game. And so what was it built for? It was built to provide a simple API for taking code and making it into parallel code. It has to do with this idea of auto parallelization. So the really big, the really ideal way of doing it would be I can write a program without worrying about parallel versus serial, just write it out like I'm used to writing my other code, and then feed it through some kind of compiler or some kind of program that parallelizes it for me. And just makes it into a parallel program. Wouldn't that be nice? There are a lot of problems that arise when you try to do that. So as far as I know, there aren't really many places that are trying that auto parallelization approach anymore. With AI on the scene, who knows what could happen? That could actually be a breakthrough in that domain. But up until recently, parallelization is still something that has to be done by programmers, by people to make it work. So OpenMP is one of the many tools that are available to make that happen, and it's also one of the most common. I would be willing to bet money that most, if not all, of the computers on that top 500 list that we were looking at are using OpenMP on the programs that are running on their machines. It's very common, it's very popular, and that's despite the fact that it only works in 3 languages, one of which is Fortran, which might seem really silly, but actually Fortran does still have its uses. I would say Fortran is probably more in use in HPC than in a lot of other areas, although we're not going to go there in this class. They haven't stopped updating Fortran. I know it's kind of a meme, kind of a joke, of how old it is, but Fortran has objects now, which was a mind-blowing fact when I learned about it, but it's true. You can do object-oriented programming in Fortran. So they haven't stopped working on Fortran. It still is a thing, but we're, of course, going to focus on the C and C++ versions for this class. This is a slide that I think I've already showed you once in a previous class, showing the way that OpenMP works. It uses the fork join execution model where there is a master thread. That is the thread that gets spawned up when you first start your program. So every program has at least one thread, right? That's the master thread. Whenever you hit one of these directives, which are pragmas, we'll start to see those when we go through some examples here in just a little bit. As soon as you hit one of those, it'll spawn off however many threads it has been told to spawn, right? Usually we have that say, we have that control over how many threads it's going to create. And then once it reaches the end of it, so there's two ways that you can hit one of these. You can explicitly put in a barrier here that says, hey, wait, make sure you wait for all these threads before you move on. But also, if you just hit the end of the pragma, that's an implied barrier. Again, see examples of that when we get to the code examples here in just a little bit. OpenMP is primarily used for data parallelism, and that's because it is a shared memory program. It relies on the shared memory programming paradigm. The other framework that we're going to look at next week, MPI, which we're going to be using on homework 4, is using the distributed memory programming paradigm. So if you're interested in doing more kinds of parallelization that don't fit into data parallelism world, MPI is perhaps a better fit. But there are so many problems that work well with data parallelism. So OpenMP has a lot of good uses. All right. I'm going to jump right into it, actually. Today is meant to be a lot, sort of a work along kind of a day. There are code examples on the website, which if you want to run them on your own machine, you can. If you want to run them on the Linux lab machine, which is probably what I'm going to do just because it's sort of what I expect people to be doing for the homework assignments, then do that as well. But if you want to run it on your own machine, if you're using Linux or Windows Subsystem for Linux or something like that, you'll probably have to install the libopenmp package first, or your package manager, whether that be apt or I forget what the other ones are. Yum. There's a bunch out there, but it's standard, right? It is very easily accessible. It's not difficult to install. Every major Linux distro that I know of has a package for OpenMP in its package manager. So if you want to use your own personal machine for this next homework assignment, it would be pretty simple and straightforward to do so. But I'm going to use the Linux lab machine. And I would encourage you, again, to kind of follow along with these exercises if you have your computer. And if you don't, no big deal. I forgot to warn you all that we would be doing coding exercises today. All right. I'm going to load it up on the window. If you want to use the console and just log in through shell, that's also totally fine. It's just easier I think for the recording and stuff for me to use the windowed version. It's a little more presentation friendly. I am going to fire it up with at least a few cores today because we are doing parallel stuff, right? So I really want to have at least a few cores to play around with. And I should probably set this to be at least a couple of hours as well, so it doesn't time out on me when I'm in the middle of doing stuff. And so as this is kind of queuing and launching itself, we're going to take a look at a few different ways that we can do parallelism with OpenMP. It works really well with loops. So it can take a for loop, for example, and parallelize that for loop for you, which essentially is taking that loop and breaking it up into chunks, which are then done on the respective threads. But it can also take non-loop code and parallelize that for you as well. So if I have a block of statements that is 10 statements long and they're all independent of each other, and I want them all run on different threads, it has that capability as well. There's a lot of flexibility, and while I'm not going to be able to cover all of it in today's class, there just simply isn't enough time, I want to point out that all of the examples that I'm running from today are from this OpenMP tutorial, which is from the Lawrence Livermore National Laboratory. So every example that I'm about to show you is from this little tutorial, and this is a great reference as well. I would encourage you to have this handy as you're working on homework assignment 3, just as a reference if you need to look up what any of the OpenMP stuff is doing. And we'll be sure to take a look at the homework assignment 3 code a little bit later on today as well. But for now, I think my session is loaded, so let me go ahead and hop in. First thing I need to do is download the code examples, which I'm going to do through the browser. Again, if you know how to do it through the command line, you're more than welcome to do so, but Canvas can be a little finicky, in my opinion. So the examples are right here on the calendar page for today, right underneath my slides, these OpenMP examples. So I'm going to go ahead and download those. And they need to be extracted. So I'm going to hop over to my downloads folder real quick and extract them, even though I could probably have done that on the command line as well. All right. There they are. So I need to go into my downloads folder and OpenMP examples. Perfect. So we've got 1, 2, 3, 4, we got 7 little code examples in here. The first one we're going to take a look at is a simple, very, very simple hello world example. So let me go ahead and pull that up in a text editor real quick, and then I'll talk about how we can compile and run this guy. Here's the include that you need at the top for any program that's using OpenMP. Make sure you get that header in there so that you can reference all of the OpenMP functions that you're inevitably going to need to call. We're creating some variables for how many threads we want, as well as a thread ID. And then this is going to do a function call to the OpenMP API, just saying, hey, how many threads are there? And then just print out which thread I am. Only the master thread is going to do this guy. So only the master thread is going to print out how many total threads that there are. But actually, I think the most important thing to pay attention to in this program is this right here. That's our first example of a pragma. So notice that it is bracketed, just like a loop would be or a function would be. And then OMP is just some syntax magic that needs to happen. Parallel quite literally means that we want to do some parallel computing in this next in this section, in this block. And then the private keyword indicates that these two variables, nthreads and TID, every single thread that gets spawned is going to have a private copy of those threads, of those variables, sorry. So those are not going to be shared variables. Those will be private variables that actually allocate memory for those variables for every single thread that gets created. So let's go ahead and compile and run this guy. You can use I included on the slide, actually. It's a good time to go back and talk about that on the slide. I'm not going to worry about tau right now. Probably won't mess with tau at all today, to be honest with you. But especially for the homework assignment, if you really want to get all those performance statistics out of your executions, you can use tau with OpenMP. It's very similar to the way that you had to set up and use tau on the previous homework assignment. You have to add this is a different one. Last time it was tau threads or something like that. So now it says tau OMP, and the make file, I believe, is in the no, it's in a slightly different place as well because it is also tailored to OpenMP. So you might need to throw these again into your bash RC file or into a script if you want to use tau on a homework assignment. But if you just want to compile and run the code and you're not worried about using tau and all that fun stuff. The main thing to keep in mind is that you just have to remember to pass the -f OpenMP flag, which I uh, am fairly certain will. I'm fairly certain it'll work here. Let's see. OpenMP. We may have to add that anyway. We'll see. We may have to do the module add statement anyway if this doesn't work. -o hello OMP. Let's see. Yeah, no, it worked. Great. And so the binary is there on the left. I called it hello. Sorry, this text is pretty small. I can't really figure out how to make it. Oh yeah, there we go. That probably helps. Great. And so now we can actually run this. There's no arguments or anything necessary. What's interesting though, and I think what the slide asks you to do, is to run it a couple of times. Don't just run it once, but run it a couple of times and notice that, well, I kind of got lucky there on the first two. It actually gave me the exact same order, but this last one finally illustrated what I was hoping it would do, and gave me a different ordering of the threads. So there's no guarantees, right? There's no guarantees that these threads are going to get spawned up and make its way through code in the exact same order. Why not? Why can't we make that guarantee? What's happening to cause these appear in orders? Any ideas? Yeah. Some of it could. So I'm presuming that the threads are created in the order that they're numbered. I guess that's maybe not an assumption to make. It seems like it would be. I don't know why they would make threads in a random order. But then the question to me is, if I'm making them in 0, 1, 2, 3, 4 order, why aren't they finishing in 0, 1, 2, 3, 4 order? It could just be because some of the threads are finishing faster, but really, why? It's kind of what I'm trying to get at. Why are some threads finishing faster? I think there is a legit reason. Yeah. Bingo. Yeah, I think that's almost certainly what it is. The operating system can come in at any time and say, "Hey, I got to swap you out. Something else has got to happen." It's happening all the time. We don't see it, right? The operating system is continuously switching threads in and out, not just for our program, but to keep the operating system itself, right? Pulling the mouse, pulling the, redrawing the screen, all that fun stuff the operating system has to do. So I think that is almost certainly why we don't get the same order back out every single time. Although it is interesting to me that 0 and 4 happen to almost always be first, and it's just the final three that seem to change. I'm a little bit that is interesting to me. Maybe these two can finish faster than a context switch happens. The other three, the remaining three, are the ones who are feeling the brunt of the operating system. That one I'm not quite so sure as to why we're seeing that behavior, but could be something interesting to investigate, perhaps on a future homework assignment. One thing that we didn't see, one thing that I didn't show you, so clearly there are 4 threads here, right? Why did it choose to do 4? I didn't see the number 4 anywhere in that code. There's no arguments, right, that say, hey, spawn 4 threads. Well, there's 4 cores on this machine, and it knows that. So I think that's why it's spawning 4 threads. But what if we don't want it to be 4 threads? What if we only want it to be 2 threads? There's a few different ways that you can change that, which I don't think are on the slide, as a matter of fact. I should have probably put them on the slides now that I'm thinking about it, but we can change the number of threads. This is the more common way that I'm used to doing it, with an environment variable. So there's an environment variable OMP num threads. I believe you can also do it within the code itself if you actually wanted to change the number of threads And we may see an example of that a little bit later on. But the way that I'm most used to doing it is with the. Oh, are you gonna make me do it myself? All right. I tried to copy paste it and it didn't work. So if I wanted 8 threads, I can simply run that export statement and rerun this guy. And hey, there we go. Now I've got 8 threads. And we see a bit more variance now too, which is interesting. And kind of makes sense, right? We only have 4 cores. So now there's clearly some contention happening where I've got more threads than I've got cores to run them on. So some of them are just after until one of the other threads finish, or they can skip along to the processor. So that makes a lot more sense to me that we'd see a bit more variation. Although thread number 1 does seem to be doing a pretty there, thread number 4 won that time. And remember that this is always the master thread, thread 0, which is why you always see thread 0 is almost always immediately before this number of threads statement gets printed out. Yeah, cool. Any questions so far? I know this is just a simple, I promise they get more complicated, but questions so far? All right, let's keep going then. This one. All right, so a more realistic example of OpenMP is with for loops. So we're going to take a look at a vector addition example next, which is, I believe, aptly named in here as OMP vector add. We, of course, need to compile it first. Actually, we should take a look at the code first before I compile it. Let me do that. You can compile it if you want to. That's totally fine. We've got a couple of constants defined up here. N, which I believe is the size of our vector, which we're going to be adding. And then there's one called chunk size, which I want to talk to you about a little bit later on as well. Here you can see we're making 3 vectors. So we're going to take A and B and add them to C, I believe, is the goal here. And now when we get to our parallel section of the code, notice that we still have this pragma OMP parallel like we did in the last one, but then we have a second pragma immediately before the for loop. So this is specifically telling OpenMP that this for loop is what we want to parallelize. But let's back up for a second and notice that, hey, we've got a little bit of a different clause here. This one doing what I hope you would expect, saying that, hey, these variables are all shared. So there's only one copy of those variables, which is important to know, especially if we're worried about critical sections, race conditions, things like that. In this case, I don't think we are worried about that here. This chunk size is only ever going to be read from. I don't think it's ever being written to, so we don't have to worry about race conditions there. And while the C array is being written to, we see there's an assignment statement here. The way that the data is going to be broken up, since it's an array, right? We're only going to let threads write to one section of that, and there's not going to be any overlap, so we don't have to worry about race conditions there either. So we can share those, and of course, better to do that when we can. That's going to consume less memory. But notice that the one private variable is now our loop variable, I. So this is a classic example of data parallelism. We're taking these vectors and we're breaking them up and saying, hey, you compute this part of the vector, you compute this part of the vector, you compute this part of the vector. So each thread is going to get its own segment of the vector to compute. How are we breaking them up? That's where the chunk comes in. We're actually using this chunk size to specify exactly how we want this vector to be broken up. So up at the top, you can see that n is defined as 1,000 with a chunk size of 100. Quite literally means that I'm going to take 100 units from the vector, so 0 to 99, give that to the first thread, then 100 to 199, give that to the second thread. Varying that chunk size can make a big difference on performance. Why? how's that chunk size going to affect our performance? There's another word that begins with a C that I think is something that would be wise to consider when determining the chunk size. Yeah. Cores. So yes, because you don't want to have more chunks than you. Well, I'm sorry, coarsening. Oh, I thought you said coarse. Coarsening? What do you mean by coarsening? Oh. The size of the chunk definitely matters. Yeah, but what is it about that size that is going to influence the impact of our code? Where does what? Sorry, cache. There you go. That's the C word I was looking for. Cache. Uh, we want that chunk size ideally. Well, obviously the data type matters as well. Is that kind of what you're going for with the coarsening? We want the chunk size to hopefully fit in a single cache line, ideally, right? That would be the best case scenario. But how big is a cache? That's going to vary depending on system to system. So you really need to know a lot about the architecture of your system to make those kinds of decisions. I guarantee you that on the supercomputers that we were just looking at, these numbers are very well known for those particular systems on how they can most efficiently fit this data into cache. But, I think it also makes sense that the chunk size should hopefully evenly go into the number of things that we have, so there isn't a thread with an uneven chunk of data at the very end. Also consider too, I think my number of threads is still set to 8, but with the way that these constants are set up right now, I've got 10 chunks. So what does that mean? Well, I'm going to spawn up 8 threads, and they're going to get the first 8 chunks. And then whichever 2 get done first are going to get those last 2 dangling chunks, which, does that make you feel a little awkward? Maybe I should evenly divide this up so that there's an even number of chunks for the number of threads. Or at the very least, it should be every thread gets 2 chunks, right? Or something like that. So that there isn't it's load balancing, so that there isn't an uneven amount of load being distributed. But that's how it works. It actually is going to break up all of these vectors, all these arrays, by the chunk size that I've specified here. So I think, um, yeah. And then this loop will be executed in a parallel fashion, much as you would hopefully expect, where um, the first chunk gets assigned to the first thread, the second chunk gets assigned to the second thread, and so on and so forth. This no wait at the end, that's a clause that says typically when you hit the end of the parallel section, there's an implied barrier there. I think it said that on the previous example or hello example that all threads are going to wait before proceeding on. If you include that clause no wait, though, it says, hey, you don't have to. So if the master thread gets done first, which is the only thread that's going to run any of the non-parallel code, it can proceed on even if the other threads are still kind of doing their thing. And one other thing that's important to note here is that OpenMP has its own timing function. So OMP get W time for get wall clock time is a function that does exactly what it would suggest. So if you take it once at the beginning and then you take it once at the end and do a little bit of arithmetic, that can be a perfectly reasonable way to just get a simple performance metric code. Not going to tell you like shits and stuff like that. You gotta use profilers if you want to do that. But if all you're interested in is just runtime, that's a perfectly reasonable way to go about it. Let's try it out. Let's play around with this one a little bit while we're at it, because we can tweak some of these values and variables and see what effect, if any, it has. Also, I guess I should note, I should be using that srun command here, but I didn't feel like it. It's kind of a pain in the butt. For the homework assignment, please use the srun command. We're just messing around. I'm not actually going to be plotting any of these times or anything, so I'm not as concerned about it. But please continue to use the srun command to make sure that you're getting an isolated environment and you're not just you're not running on the same system as a bunch of other people. because that'll conflict with your results. All right, let's compile this guy. Uh-oh. Oh, that's just a warning, so I'm gonna pretend like I didn't see that, because it did in fact compile. Great. It just wanted me to put in the return type for main. That's not that big of a deal. And okay, it's not showing us the result of the math. I don't care about the result of the math, right? I care more about the performance. And wow, it's very fast. Very, very, very fast. But we can, of course, do something about that if we want to. We can tweak this code a little bit. In fact, I might spend a little bit of time tweaking this code and seeing exactly what we can do. Let's really put a couple more zeros on there. Now we have a lot of chunks, right? Now each thread is going to be getting several chunks of work to do. Should hopefully slow it down a little bit. Where's my compile? There it is. Not as much as I would have suspected though. Wow, really got to crank it up to get any kind of uh is that too big? I don't want to go. I think I can do one more zero before I max out uh an int. Oh, whoops. Never mind. I already went too far. My bad. I might put the int in here too, just so I stop getting that warning. But yeah, playing around with the chunk size is also an interesting thing that we could try and do. Oh, really? Okay. Well, I greatly overestimated how far I could push this, I guess. Um, oh, how is that? I okay. That's only it's only 10 million. I feel like that should very easily fit. I'm a little confused now, but we'll just keep going until it actually gives us a decent result. Which is a lot smaller than I thought it was. Okay, apparently that's as big as I can go without seg faulting it. I gotta feel like I could push it farther, but I'm not gonna take the time to do that now. Maybe after class, that one might keep me up a little bit at night tonight, to be honest with you. I might be thinking about that one in bed, but we don't need to worry about it right now. What I do want to do is maybe play around with the chunk size a little bit before we move on to the next one and talk about. So I hope that doing this we would see as being a very bad thing. Chunk size of 1 means that each thread is literally getting one element from each vector and adding it to the vector. The overhead spinning, right? All those different threads grabbing those different chunks, I would expect to be have a fairly negative effect on runtime, and you can see that it in fact does. So that's with the chunk size of 100. Switching it to 1, the cache effects from that would be most of what we're seeing there, right? Loading one value in at a time is just not effective use. So by changing that chunk size, you can really kind of get a feel then for what your cache is looking like. It was at 100 before. Let's try 1,000. Let me put in the dang int so it shuts up about the warning. Okay, so yeah, cranking it up to 1,000 had a positive impact, right? These are very informal. Still kind of showing that the way that you write the code is definitely going to have an effect on performance. If we're running giant vectors, giant matrices, which they are on these big machines, then that's going to add up. That's going to matter. It's going to make a big difference. One other thing that I think is worth playing around with, and then I promise we'll move on to another example. Um, there's a clause that I didn't mention down here. This one for scheduling. So this schedule clause has two different options. It was set to dynamic. The other one, of course, the opposite of dynamic would be to set it to be static. What does that mean? Well, dynamic is exactly as I explained it, where as one thread finishes, it just grabs the next one in line, right? When it's statically scheduled, that means it's going to schedule them all up ahead of time. So thread 1 is going to get, chunk 1, chunk 10, chunk 20, and thread 2 is going to get chunk 11, or chunk 2, oh gosh, I can't do this right. Chunk 2, chunks 12, chunks 22, so on and so forth, right? So all of that's going to be predetermined. That static scheduling is going to be happening before any of the threads actually get fired up. Which pros and cons, right? Pros and cons. Dynamic seems like maybe it would be better at load balancing because it's adapting on the fly. But then there's extra overhead involved. Maintaining positioning and stuff like that is going to be potentially better with static. All dependent on the application, though, as to how much it actually matters, how much it actually is going to affect our performance at the end of the day. You can see here that it didn't seem to have that much of an effect at all. Might not be much of a big enough of a program to. Oh wow! You can also see that the numbers are varying significantly between runs. Maybe I should have tried this a little sooner. Got some wild swings there, which is interesting. Um, None of them are as high as this one, though, from before we messed with the chunk size, which is also interesting. But yeah, there's lots of little things like that you can tweak. Lots of little knobs and levers that you can push and pull and turn to adjust these programs, and that's what high performance computing is. Really, is making sure that you've got all those knobs and levers at the exact optimal position. Any questions on this one? Before we move on, we'll look at some more examples. No. All right. Let's keep going. Sections, yes. So this is parallelization, but without a loop. So we're parallelizing non-iterative code. There's actually a few different ways you can do this. I'll show you a separate example as well. But the first example that we're going to be taking a look at with sections, I'm not worried about the math so much. I'm more worried about the parallelization stuff that's happening down here. Here's our parallel section. You can see that all of the vectors get shared. And then here is the second pragma. So the parallel is what spawns the threads. And then this is really the kind of parallelism that we want. So not a for loop this time, but now we're parallelizing it with different sections. You can see we have two different loops here. So what that means is that one thread is going to take this for loop, one thread is going to take this. So the section pragmas are saying that I want these two distinct sections to be run on different threads. It doesn't have to be for loops, right? It could be any sections of code that you have. Although this is, I think, a good example because these two loops have the same number of iterations and are going to be roughly the same size in terms of that's important to keep in mind. But one thing to also keep in mind is, well, okay, how many threads do I really need to do this? Just two, right? There's only two sections. So I really only need two threads. If I have more than two threads, like right now, I think I'm still set to 8. If I have more than two threads, those other 6 threads are just sitting around chilling, doing nothing, which is a waste. That's clearly a waste. So definitely something to also keep in mind. You're never gonna want more threads than when you have sections. And the opposite also can have some negative effects. If you have fewer threads than there are sections, they will still all get run, but that just means that whatever thread finishes first is going to have to pick up whatever the next section is, and so on and so forth. So all of those sections get run. So really with this code, it's almost always ideal to have exactly the same number of threads as you have sections. This one maybe not terribly exciting to run. It doesn't even print anything, so I'm not sure I'm even going to bother compiling and running this because it would not show us anything. It's not taking the time or doing anything like that. But just wanted to show you a coding example. Um, it's a little bit different than the parallelized for loops that we saw in the previous example. And then, oh yeah, which thread executes which section? Also an interesting question. Um, and I believe it's as you would expect. The first thread picks up this one, the second thread picks up this one, and so on and so forth. Okay. This is going to be an exercise for you all to do. So I'm actually going to stop talking here for a second and let you all play around with these next couple of examples. There are two examples called WorkShare. How did I? There we go. WorkShare1 and WorkShare2.c. I want you to, I'm going to give you, this will be kind of our break slash exercise time. Do during this time as well, but I'm going to give you the next 10, 15 minutes to take a look at these exercises, play around with this code, and we'll chat about these two examples. 674? We'll say 650, somewhere in that ballpark. Hopefully that's enough time for you to hit the bathroom if you need to as well. Grab a drink of water, and we'll regroup at 650. And after we do these examples, we're going to be ready to start talking about the next ones. So we'll do that after break. You said Colorado? Clearwater. Table Rock. Close.
So the really
Awesome. Catch anything good?
too small for that.
Would be tasty?
Yeah, you,
Yeah.
hindrance.
Oh, it's hot. It's hot.
Still is pretty, so, having this, jump water.
Oh, yeah. It would have been, this week would have been better for weather-wise, but
I just saw a little, they pulled down.
yeah, oh yeah. It's still kind of warm out there. It's way warmer than it was. Awesome. It's great you get that. Yeah, it's true. At least we can get storms. Storm on team. There are a lot of fireworks out there.
Something extra. I think there's a couple of spots.
It's so hot. You probably fireworks. So, yeah.
Well, at least some neighboring, was understanding should bounce like rather trees.
Yeah. You have the smartest idea. I'll be going camping in the Smoky Mountains in August. I'm hoping it's not gonna be in London when we go there. We'll be in the mountains though. Oh, really? Interesting. Yeah, we'll be in the Virginia south, the Smokies. We're gonna go up to Philadelphia for a few days on my wife this time. So it should be a fun trip. Oh, oh, fun. I don't know that I'll be doing a lot of hiking with a 6-year-old and an 8-year-old, but we'll see if they want to do hiking. Definitely do some. Well, I guess I don't know if there'll be anywhere to swim up where we're going or not. Let me see. Let me see. My wife on yeah. Yeah, I love to try to go at least 3 times a year. Alrighty. So these two problems I had you look at are really just kind of illustrating some of the things that I already spoke to you about before the break. But the nice thing is they added in some print statements to make it a little bit more clear what's going on. Obviously, practice we wouldn't necessarily need to print out every single one of these, but it does help us kind of view what's going on. So if we take a look at the first one real quick, um, and I may move through these a little bit fast because I am concerned about making sure we have enough time to discuss the homework assignment. But this is an example that uses parallel for, so it's parallelizing this for loop. And so we already talked about how the chunk size and everything matters a lot, as well as the way that it is scheduled. So right now it's set to be scheduled in a static way. But if we, run this guy and take a look at some of the results, there's a few interesting things to notice. You can see that thread one is starting and got assigned to the chunk from looks like 1 through, well, why is 90 on there? That's a little, oh no, that actually it makes a lot of sense. I'll get back to that in a second. But then clearly you can see it got interrupted, right? Because it didn't finish 90 through 99, and then thread 6 started up and actually only got through a couple of values before it got interrupted. So we can actually see in real time that the operating system is saying, hey, I got to kick you off and schedule something else on here. And then eventually thread 4, thread 6 will come back and finish, doing all the work that they are scheduled to do. The way that it's set up right now, we've got 8 threads, but there are 10 chunks. And so with the static scheduling, you can see that thread 0 is always going to have the very first chunk and then the second to last chunk, 80 through 89. So thread 0 and thread 1, they're the ones who are doing double duty. But interestingly enough, it looks like thread 1 managed to finish before thread 2, even though it had to do 2 chunks. That can certainly happen. But one quick and easy thing to take a look at is just changing this to dynamic. And I already played around with the chunk size a bunch, so I don't really feel like I need to necessarily do that again. But it is interesting, I think, to kind of play around with the chunk size a little bit and see what effects that has. But just switching the scheduling up a little bit, and you'll see that we get very different results in terms of who's doing what. So now you can see thread 2 managed to grab the first chunk somehow, and thread 7 is doing, that would be chunk 3 from 20 through 29. Who's pulling double duty is kind of what I'm looking at. It looks like thread 0 is still somehow managing to do 2 chunks, 3 chunks even. Wow. So thread 0 doing 3 chunks in this this particular run. Before thread 3, this is the first time I think thread 3 even shows up. So thread 0 managing to do, oh no, there's thread 3. Well, thread 0 managing to do almost 3 chunks before some of these even really make much progress at all. Kind of interesting. Another interesting thing is if you run it again, right, you're going to see that different threads are the ones who are getting the extra chunks. So it looks like thread 2 is getting some of the extra chunks on this one. So the dynamic scheduling is always going to run differently, whereas the static scheduling, maybe I should have run that one a few times. But you'll notice the static scheduling, the threads are going to be running the exact same chunks of the vector every single time you run the program. Pros and cons, right? And one is not necessarily better than the other. They both have their pros and they both have their cons. As far as the second one goes, I think the interesting thing to see with the second example is that I ran it with, I've been using 8 threads basically this whole time, but there were only 2 sections, right? There were only 2 sections of work. I guess I didn't show that to you, but if you take a look at the code for this example, there's only 2 sections of work. So there's this for loop that'll be executed on a thread and this for loop that'll be executed on a thread. And so if we look at the results, you'll see that it looks like thread 1 is doing one of the loops and thread 2 is doing one of the loops. But they're the only ones that I see doing any actual computations, but I still have 8 threads, right? So thread 4 starts up and says, oh, well, all the sections have been spoken for, so I'm done. And thread 6 does the same thing, and thread 7 does the same thing. So those threads just pure waste, taking up, like, it's not a lot, but it's still unnecessary work that those threads are doing. So definitely important to keep in mind when you're writing these kinds of programs, how much parallelism you have going on, and make sure your program is tailored accordingly. No timings were taken, so it's hard to say exactly how much time was wasted by spinning up those extra threads, but you certainly could, and that would be an interesting thing, if you wanted to. I don't know if this would be the best one for the homework assignment, but it would be an interesting thing to kind of play around with and explore perhaps at one point. There are a couple of other directives that I am going to run through real quickly because, as I said, I'm interested in getting to the homework assignment. We actually won't need this one for the homework assignment, so I might go through this one extra fast, but I'll show it for the sake of completeness. We can do critical sections, if I can spell it properly. We can do critical sections within our parallel sections. So here we see that we have a shared variable x. We want to make sure that when we update it, that is in a critical section so that we don't have classic least condition. So one interesting thing to do here would be to run this code with the critical section and then come in and take the critical section out and see what happens. See if that changes your value of x. I'm not going to do that though for now. I'm going to move on to the next one because I believe the next one is one that is a bit more relevant to the homework assignments. Reduction. So if you've ever done reduce, which used to be big, I guess it probably still is. It doesn't seem like it's as popular as it used to be, but I'm sure it's still around with architectures like Duke and stuff. But it's the same idea. We're collecting data from a bunch of different places and combining it into a single value. In this case, the places we're collecting that data from are all of our different threads. So we can have our threads compute a partial value and then use a reduction to collect all of those and combine them into our final value. This is very, very useful, and I believe there is an example of this on our homework assignment that we'll be taking a look at here in just a moment. But let's take a look at this simple reduction example really quickly here. We've got two arrays, and our parallel section is right down here. Notice this time they took a little bit of a I don't know if you call it a shortcut or not, because the past examples we saw that the section was its own separate directive, and then the for was its own separate directive. You can actually combine them and do them all in one big long directive, which is what they're doing here. Pragma OMP parallel for, and then we see all the shared variables and stuff. But at the very end is the part that we're care about, at least in this particular example. It's saying there's a reduction here where we want to take, in this case, we're keeping a separate result for each thread. But at the very end, once this loop is finished, we want to collect all of the partial results, and then this can be addition, it can be multiplication. There's a few other ones that it can be as well, but this is just the operation that we want to perform across all of those partial results. We reduce them down to our single final result. So that's what's happening in this particular case. But what I would like to do, since we only have about an hour left, is talk about the homework assignment. So let's talk about, we're doing a simulation. In particular, we're doing, sorry, it's bothering me that this isn't displaying properly. We're making a model of something that exists in the real world. So the digital twin, I don't know, that phrase seems a little outdated to me, but this is a real thing that actually exists in the world, and I'm trying to recreate that situation on the computer, trying to simulate it on the computer. There's two classic ways that you can do this. Time steps is what we're going to be using. In this particular example, I might talk a little bit more about discrete event simulation in a future class, but time step is what's more relevant to us for um, uh, the upcoming homework assignments. And so what we're doing is we're just going to be repeating our simulation from time step t of I to time step t of I plus 1, where we have control over how big that time step is, and that's going to have a big effect on how accurate our results are. The smaller the time steps, the more accurate we'll be. But of course, that's the more computations that we have to do as well. So there's that continuous trade-off there. So lots of places where this can be useful and will be used. Lots of different areas. So protein folding is a classic one. Climate simulation, that's what we talked about on the very first day of class. The n-body problem. Keep that one in the back of your mind because that's homework 4. So we'll be talking, that's another example of continuous simulation we'll be talking about on the final homework assignment. But the one that we're concerned about for this particular homework assignment is more aligned with not fluid dynamics, but heat transfer, I guess, which isn't actually on this list. I probably should have added it on this list. They're not all based on time, but a lot of them actually are based on time. And these are all examples of real problems that, are computationally intensive that we are trying to solve. Climate simulation is, of course, a very big topic that is being run on many of those supercomputers that I talked about up at the top of class. And really the idea is, if we can't sit down and figure it out ourselves, can we just have the computer crunch it through with as many of the variables as possible to predict the outcome? The smaller the time step we can use and the more variables we can include, of course, the more accurate our actual simulation model is going to be. This is a repeat of a slide that I was going to, but the reason why it's here is because it's relevant to our upcoming homework assignment. The kind of parallel execution that we're going to be talking about in the upcoming homework assignment is an example of nearest neighbor grid computation, where if I want to know the value at this particular point, I'm going to have to get the values from either it could be just the 4 cardinal directions, or some simulations might require the diagonals to be included in there as well. But think about the effects that it's going to have on parallelization, right? Especially if we're trying to decompose this into chunks. If this is a 2-dimensional array that we're breaking down into blocks, any of our grid points that are well within that block, very easy for us to compute. But if I'm on the edge, then, ones that are on the edges of these blocks then require some communication, which, remember, in our case is going to be shared memory communication. So the good news for us is that OpenMP takes care of that for us. We don't have to explicitly say, hey, go fetch values from our neighbors. OpenMP is going to orchestrate all of that for us and make sure that every thread has the data that it needs to perform whatever is being requested of it. So this is, and you'll see when we start up take a look at the homework assignment here in a little bit, that this is what we're doing. This specific problem that we are solving is this one. Laplace's equation. You can see the math board up at the top. It's a differential equation. The good news is for this class, you don't need to worry about the math so much. I think you'll actually be pleasantly surprised at how not math heavy the program is that I'm giving to you, right? The solution, while we certainly could talk about differential equations and would be appropriate to do so for this particular problem, it's actually not necessary to talk about the code and understand the way that we're going to be solving this particular problem. But I think it is important to understand, well, what the heck is this problem that we're trying to solve? I believe I've kind of talked about this actually in class already, but just to go into a little bit more detail, imagine this is a metal plate or some other kind of substance that is maybe floating in outer space, right? And this side is close to the sun, or is facing the sun, and these other three sides, maybe not so much. And so we know what the temperature is on this side and this side. So we know what the temperatures are on the border. It's a boundary problem. So that's the mathematical term for this kind of problem. It's a boundary problem. We know what the values are on the boundaries, but what we want to know is what the values are in the middle. So we have to use the information that we have, these boundary values, to help us understand what the temperature, or yeah, in this case, temperature, is going to be in the middle of this particular plate to make sure it's going to, withstand the heat forces that are acting. There are two different ways that we can do that. The way that we're going to see on the homework assignment is a very analytical approach. And that works really well for easy shapes, which in our case, it's going to be rectangular. That's about as easy as it gets when it comes to analyzing shapes, especially on the computer, because 2D arrays work very nicely for those kinds of situations. Actually, to be more specific, the iterative solution is what we're going to be looking at. The nice thing about the iterative approach is it's consistently applied over the entire surface. Very easy, very direct to compute the values for the entire surface. Whereas the Monte Carlo simulation, which I kind of touched upon in an earlier class, and we're going to talk about it a little bit more today, is good when we only need a solution at a few points, but doesn't work well if I try to use it across the entire surface because there's a degree of randomness. And so, I can get a good answer for the middle points without having to worry about all the points around it, without necessarily having to compute all the points in the entire grid. But if I want to apply the Monte Carlo approach to all of the points in the entire grid, it ends up oftentimes being more computationally heavy than if I just use the iterative approach, which is what I'm going to show you in just a few moments. I'm a big fan of Monte Carlo simulations, though, so there's a reason why I talk about this, and they are useful. They certainly are useful for a non-regular surface like this, where you can see that there are some rectangular portions. We'd probably try and use sort of an upward approach, right? I could maybe get away with an iterative section on this rectangular bit and maybe up here on some of these rectangular bits. But for some of these more irregular parts that are sticking out, it might be appropriate to use Monte Carlo approach for them. And just a recap of what the Monte Carlo approach would look like for this particular problem. We start at the point that we care about. So if the point that I want to know the temperature of is right here, we start here, and then we randomly decide which direction we want to go in, either up, down, left, or right. And we keep doing that. So I go left, and then I say, all right, I'm going to randomly choose again, go down, and then maybe go up again, and go down again, and then right. But eventually, I'm going to randomly end up at one of these boundaries, which are known. So we know what the boundary values are. And I'll write that number down. So I take my first random walk, and I end up here. So I'll write down 30 Kelvin on my list, but one more is not good enough. The Monte Carlo simulation, our results get more accurate with the more walks that we have. Although there is a trade-off there as well, right? Because it will eventually plateau. And so after a point, you're kind of wasting your time because you're already like close enough to the answer that doing it a few million more times isn't really going to get you that much more closer to the answer. So that's kind of what I was referring to on the previous slide, where this is an important point. Slow to converge, but does eventually converge on our correct answer. But anyway, we're going to run a random walk, at least 1,000 times or 10,000 times, or it depends on the problem we're trying to solve, really, but a bunch of times. And every time we hit the border, we'll write down which border we hit and the temperature associated with that border. So if I'm down here in the corner doing these random walks, you would expect that I'm going to hit this value and this value very often, the 20 and the 30, and I'm not going to hit the 400 or the 600 as often because they're much farther away. Of course, sometimes I might get random walks that mosey on up there and hit those values, but not very often. So what we do then is we sum them all up and average them together. That's going to give us our value for the point. Because this particular point is super close to these two, I would expect it to be in that intuitive perspective. It kind of makes sense how it works. Let's talk about it from a performance perspective, though. There's a real problem with running Monte Carlo simulations, and it has actually somewhat to do with what we talked about today. With the examples we looked at today, we talked about the chunk size, and we talked about how important it is to make sure that we've got relatively similar amounts of work to do for all of our different threads. With the Monte Carlo approach, though, that's really hard. Consider that one random walk might take a couple steps and be done. One random walk might come up here and spin around 100 times and then finally make its way. And one could, theoretically, randomness could never end, although in practice, we don't really worry about that too much, but the loads are different. Each walk can be done independently, but each walk is going to be vastly different in terms of how far it's. So load balancing Monte Carlo simulations is tricky. It's very tricky. These points down here are going to have much faster random walks on average than if I pick a point that is more close to the middle. It's going to have longer random walks on average. So that part of the parallelization can be very complicated, very difficult to work with. You can also parallelize it. I was kind of getting at this earlier. You can also parallelize it within a single point, though. If I'm just interested in this point and I want to do 10,000 random walks, I could do each one of those walks on a separate thread. Or more realistically, I'd probably do like 1,000 per thread, right? Over 10 threads. And that might get me pretty good load balancing, but it's still very possible that the first batch of 1,000 walks is going to be a lot longer than the second batch of 1,000 walks. And we have no way of knowing that because it's random, right? Those walks are random. So we can't necessarily predict that ahead of time. Of course, the law of large numbers and stuff kind of helps us out here, right? Over a large body, over a large number of walks, we do expect those to be roughly the same, but there's no guarantees. The randomness means that there's no guarantees. So actually, this would have been a more appropriate slide for me to have up when I was talking about all that stuff. But yeah, we can parallelize it in two different ways, via the individual grid points and also via the walks themselves. That double parallelization is kind of nice compared to the iterative approach that we're about to look at. And we already talked about this a little bit in a previous class, but just to very quickly go over it again, random numbers in parallelization is a tricky problem. Fortunately, though, at least for the sake of it, I'm not going to go through the stuff that I did last time. You might remember the diagram where we used multiple seeds across different threads. That was actually, I think, on the prior exam. But for the purposes of the homework assignment, the standard grand function, while less than ideal in most parallel contexts, actually is sufficient. It's okay. We don't care about whether it's cryptographically secure. We're not worried. We're not doing crypto or security or anything like that. So for the purposes of this assignment, which, as you can imagine, I'm kind of hinting, there's the Monte Carlo aspect to this assignment. Using the typical rand function is adequate. But let's talk about the assignment, because I think that might be the most important thing that we discuss today. I want to pull up the code and show it to you and walk you through it. It is significantly more complex than the examples that we have been looking at so far today. So I think it's very important that you all understand exactly what it is that we're getting into, and then we will, of course, take a look at the questions that I'm going to ask you to investigate as well. Excuse me. I gave you a make file here, which this might be out of No, this is okay. Actually, it's not out of date. It looks fine. Yeah, this is for if you don't want to use tau. So if you're not using tau, remember gproof and parallel doesn't work. So you can't use gprof. Perf, I think, does do relatively well with parallelized programs. If you really want the best in-depth statistics, though, I think tau's the way to go. So refer to the instructions it's on the homework assignment as well as the slides on how to load up tau and use it with OpenMP. The wall clock time, though, that I mentioned on some of the previous examples is already baked into the assignment, and you're welcome to use that as well. I don't have a problem. If you absolutely hated tau and you never want to see it again, you actually don't have to use it on this assignment if you don't want to. I'm not requiring that. You can just use the wall clock time. That's perfectly acceptable for me. You may have to tweak this make file though, depending on your goals and what you're trying to investigate. Uh, what's this script about? I'm not sure I even remember what's in this script. Oh, okay. Yeah, I don't know how useful this is, but you can, of course, modify this to suit whatever your desires are if you want to run it with a bunch of different thread numbers, or tweak this to set up whatever experiments you're planning to run. But the real important thing that I want to walk through with you is the code itself. And this is a much beefier program than, as I mentioned, the ones that we were looking at before. Here is the region that we're setting up. It's actually a little bit different than the diagram slides, but not that much different. 3 of our borders are set to be 100, and this one is set to be 0. And our problem then is to figure out, okay, if these are the temperatures on the outside, then what are the temperatures all throughout this plate, all throughout the middle section? That's going to be a 2-dimensional array. But the way that we compute this is and so, yeah, we know how 2-dimensional arrays work and how indices work, so I don't think we need to worry about that too much. But here's how we're actually computing these values. We're going to this is just the average, right? Take the average of my north neighbor, my south neighbor, my east neighbor, and my west neighbor, and average them together. But now, wait a second. Doing that once isn't going to consider that, especially if we imagine the very first iteration, what are these interior values set at? A few possible options. They could just be up 0. I think it actually sets it to the average of the boundaries, what it initializes the center values to. But regardless, if I just take the average of my 4 neighbors once, you call it a day, it's not going to be very accurate. The values are going to change pretty significantly from the initial value to that first average that are computed. And so we're going to repeat this. I'm going to go through, take the average of my neighbors, and then say, hey, what is the biggest difference in temperature that I found, right? From where I started to where I am now. And if it's bigger than some threshold, which we're, I believe, calling, it's called epsilon in the code. It's down here somewhere. Yes, it's called epsilon. So if the temperature change from one iteration to the next is greater than epsilon at any one grid point, it doesn't have to be all of the grid points or even some of the grid points. If even one of the grid points is changed by more than whatever epsilon is set to, then I'm going to do the whole thing over again. Iterate through the entire grid space, average my 4 neighbors. That'll update the temperature again. Hopefully, the second time around, the difference will be less than it was for the first iteration. And then the third iteration will be even less, and it'll eventually converge, right? And so we're saying convergence happens when all of the positions within our grid are within this epsilon range. But let's take a look at the code, because there's a lot of parallelization, a lot of sections going on here. These are just setting everything up, printing out some information. here's our first parallel section, and you can see there's a reduction in there already, taking the mean of the values. But this is just this is just initializing the boundary conditions. So you can see we initialize that would be the left boundary, the right boundary, and then bottom and top boundaries. This is where we're going to compute the initial value for the interior grid points. Again, all parallelized. So all these loops can be done in parallel, but you can see that I'm taking the average of all of the boundaries, basically, averaging those together. And then finally down here, we're initializing all of the interior grid points. You can see we start from 1 up to strictly less than m and n minus 1, which are my grid dimensions. So that's what we're assuming our initial temperatures are going to be. We haven't actually done any nearest neighbor computation at all yet. This is all just setup that we've done. If we keep going though, this is where we get to the good part. We actually have 2 arrays here. Perhaps I glossed over that point, but it's important to understand that we have 2 different arrays here, one of which represents the previous iteration and one of which represents the current iteration, so that we don't overwrite our values, because we're taking our nearest neighbors, whatever value we compute for ourselves based on our neighbors is going to be used as a neighbor in the other computations, right? So it's important that we keep that old grid value and the current grid value. So I believe U is it says it in the comments. Yeah, U is the previous iteration and W is going to be the current iteration that we're on. So when we get down here to the actual, exciting part of the program, we're first just copying, right? Copy the current iteration into the previous iteration. And here is our fun little nearest neighbors. So take a look up, down, left, right, average that all together, and store that into the current array position. You can see this fun little note here that we can't do maximum as a reduction operation. So we actually have to go through and manually see what the difference is between the last iteration and the current iteration. So we're actually going through and taking a look to see how much the temperature changed at each individual grid. So at every iteration, you can see how much the temperature changed at each individual grid point. And that's what's going on here with this particular if statement. So we're taking the difference between the last iteration and the current iteration, and then keeping track of the largest difference that we can find. So finally, we're going to check. Oh, we got a fun little critical section in here for recording the maximum, so that we don't mistakenly find, multiple maximum values at once. Erase one of them. And then finally down here, we check to see, or did I miss? There's a while loop up here. While the maximum difference that we've found is, still greater than our epsilon, which is our threshold, our tolerance level, then we just keep going. And we keep running these iterations. It's going to keep track of a bunch of stats for us, including, you can see the time hooks are already in here. I think that's important to point out. One other thing that I think is important to point out about these time hooks, printing is very slow. Printing to the screen is very slow and have severe negative effect on your timings. I think there are at least a few print statements that are included as part of the time that's measured here, but if you're ever making modifications to code or which you may end up doing with assignment, or the next one for that matter, try and keep as many print statements out of the timing as you possibly can, because they will influence the times that you see in a negative way. And in a way that I don't really care. I don't care how fast it takes to print stuff to the screen. That's not really relevant to us. So try to keep as many print statements out of your timings as you possibly can. A few, not going to make a big difference, but try and keep as many as you can. And if you want to comment out the print statements when you're doing the homework assignments, right? Um, so that they aren't interfering with your timings. I don't have a problem with that at all. I think it's important to keep them in to make sure you're checking for correctness and things like that. So that's kind of why they're there. But feel free to take them out if they're getting in your way, if they're interfering too much with what you're trying to do. And so I think it is now time to do the fun part and actually give this a go. Let's see if my makefile still works. Yes, it does. And then we can, I'll just go ahead and run this script since it's here and we can see, um, what's going to happen. This is a beefier program. It's going to take some time, especially single threaded, which is what we're doing right now. But hopefully we'll be able to notice the speed up. Oh yeah. And then the script actually writes the results out. It uses a redirect to write it out to a file. So got to take a peek at that to see. Um, so for our first run up here, oops, too far. For our first run up here, you can see that the biggest difference in temperature that it found was 18, which is far bigger than our episode. So we got to keep going. And it's telling us that after every power of 2 iterations, you know, what's the difference? And then finally it took 16,955 iterations before we finally hit our desired tolerance. And that took 10 seconds for one thread. Hopefully we would expect the same results. And oh, good. That's good. The parallelization did not affect the number of iterations it took to converge. I would be worried if it did, because ideally it would be getting there exactly the same way, just using more threads and such to do that. But notice that it took about half the time. Not exactly, but pretty darn close. And then cranking it up to 4 threads, well, that's not quite half, but still an improvement, right? So you can see that the parallelization is getting us to the answer more quickly than our serial program. Are there any questions about the actual code before I switch over to the write-up portion of the assignment? There are some, I think the code's pretty good. I think there are still some inefficiencies in it though, honestly. And I'm not sure that, I don't think it's on the write-up necessarily, but if you find some inefficiencies and you want to try even better, I think that's totally fair game to do as one of the problems on the homework assignment. Just make sure you're doing it correctly, right? If the changes you make break the code, not getting the correct answer anymore, then that's not useful to us. So make sure that any performance improvements that you try to make are still actually getting you to the correct answer. But let's switch over and take a look at the write-up itself real quick here, because there is at least one piece of it that is significantly different than the prior homework assignments. Some of these you'll recognize, right? So again, there are some things that aren't surprising here. And just like the last ones, you're more than welcome to answer some of the same questions that you've done on previous homework assignments. This is a very different problem than the problems that we solved. So I'm not worried about you doing the same kinds of questions that you did. But let's talk about this one. So this is not, I did not give you if you want to implement the Monte Carlo simulation approach and care, I think that is a very worthwhile avenue of exploration. So much so that I'm willing to give you some extra credit for doing it. So this would be a lot more code writing, I think, than any of the other ones will be. We take some significant programming to do this last one. I'm not even necessarily saying that you have to show me that the Monte Carlo simulation you wrote is better than the one that I gave you. I think that's a pretty tall order, actually, to write one that is going to perform better than the code that I gave you, for some of the reasons that we already explained, right? But if you can say that, oh, hey, I can get to these middle values faster than this code does. I can't get you all the values faster than this code does, because Monte Carlo isn't really for that, but I can get you like these 8 values in the middle or these 9 values in the middle faster than the code that you gave us gets them. That's an interesting result to me. And I'm definitely willing to give you some extra credit for taking a big swing like that. Even if you don't get there, right? We learn from our failures just as much as we learn from our successes, maybe even more so. We learn from our failures. So, if you take the big swing, I can't promise that I'll give you as much extra credit as I would for a successful submission, but I'm still willing to give you some extra credit for taking the big swing and putting in the effort. So I just want to throw that out there. I think everybody's doing pretty well, but if you're worried about, past getting a bad grade on a past assignment or maybe on this exam, which I know you don't have grades back yet, but if you're worried about stuff like that, there is an extra credit opportunity out there for you. It's hard for me to say, exactly how much the extra credit opportunity is worth. Some of that depends on how well you did and what the results are. But considering that for a solo person, you have to answer 3 questions out of these 10, and I consider this one to be a more significant question than any of the other ones, I would say it's probably worth at least, I don't know, a third of a homework assignment's worth of extra credit. Somewhere in that ballpark is pretty reasonable. And if you really want to, if this is something that you're interested in and you really want to get the details hammered down, shoot me an email. We can talk about it. More than willing to talk to you all about it. If that sounds like way too much work and you don't want to deal with it, then you've got the other 9 to pick from, and the same rules apply as the previous assignments. Pick 3 if you're working solo, pick 5 if you're working in a pair. Submit your report. And I'm going to try and get you the feedback on the second homework assignment within the next day or 2 so that you have that and use that as you work on this homework assignment. What questions do y'all have? You feel like you know what you're doing-ish? Or, yeah.
Could you explain a little bit more than the slides do about how the random walk for the Monte Carlo simulation works?
Yeah, sure.
If everything else calculates off of its nearest neighbor, then that random walk obviously isn't surrounded by complete sets of nearest neighbors. So how will you backtrack to the one in the middle to get a temperature?
So we don't backtrack. We actually, there are 2 different approaches, and this one doesn't, the nearest neighbor approach, I want to be clear, is the iterative approach in the code that I gave you.
Yeah.
The random walk does not depend on its nearest neighbors. You're going to end up visiting your neighbors through the randomness of the walk, but it's a completely separate approach. And I'd be happy to go through it again. I apologize for not doing a better job of explaining this before. I'm going to start at the point that I care about. So the iterative approach is quite literally just going to go through starting at 0, 0 and touch every single grid point. This is not. This is going to start at the point that I care about and do a random walk from here. So this is an example of one random walk where I eventually end up at this border. Okay, I'm going to do that random walk, not just one time from this point, but at least 1,000, 10,000 times, right? You would do it to until you satisfy that epsilon. That part is still relevant.
Instead, you set the temperature equal to the mean of the temperatures that you end up touching on the side.
Correct.
Okay.
Yes. So every time you do a random walk, you do it until you hit the boundary. You write that number down. So that's my answer for walk 1. Maybe walk 2, I end up here, but then walk 3, I end up here again. Walk 4, I end up here, but then walk 5, I end up here again. So I write down all those values, and at the end, I just average them up. And that is going to be the value that I use as the temperature at this point. Yeah. Yeah. Awesome. Glad to clear that up. Is there any other questions?
So you said you still worry about the epsilon piece when doing the random walk. Do you do the random walk for every point and then do the epsilon? epsilon amount?
No, so what I mean by that is that eventually these values are gonna, so if I do only 10 walks, right? Adding one more to it is gonna make that temperature change by a lot still, because there's only 10 other values. So adding an 11th value is still gonna swing that average by quite a bit. If I do 1,000 walks, adding one more number to it, not gonna swing that average by as much, right? And then if I do 10,000 walks, well, that's barely gonna move the. So that's what I mean when it comes to epsilon. Eventually, when it comes, I'm basically saying, when adding one more of my boundary values changes the average by less than epsilon, I'm done. Because the average isn't shifting enough for me to care anymore. Yeah, is that, yeah, what's up?
But at the very beginning, you might run into the same wall like 10 times in a row. Like just like
That's true.
due to randomness. So
You do have to do there is at least a minimum number of walks that you have to do. Like obviously 10 is a terrible number of walks. Nothing is going to converge to a reasonable value in 10 walks. On the other hand, the point I was kind of trying to make earlier, if the point I'm looking at is down here in the corner, I would expect that to converge a lot faster than one in the middle. Because I am going to end up at these two quite frequently and end up at these other ones a lot less frequently. And so, I might be able to get away with 1,000 or 10,000 walks and call it a day, whereas this one might take 100,000 or 1,000,000 before it's going to reach that convergence point. But there is definitely a minimum number of walks that we've done. And what is that number? Again, some of that's going to be trial and error to kind of figure out. Which is why this is worth some credit. It's worth some extra credit. All great questions. And if you are working on this and you get stuck, please write to me. I'm more than happy to answer any questions you run into, any problems you run into. I think conceptually, right, the Monte Carlo, it's not that hard to code up, but getting the performance out of it, that's kind of the tricky part. You ideally are still going to need to use some OpenMP to parallelize one of these two things, if not both. And also, that kind of reminds me of another thing to keep in mind when you're using OpenMP. It is possible to do multiple levels of parallelization, but you got to be careful about that, right? So think about like I don't know if this is relevant to the Monte Carlo, but think about like a nested for loop situation where I want to parallelize both the outer for loop and the inner. You can do that. You can have OpenMP parallelize both, but you got to be careful because it's going to want to spawn the number of threads for the outer loop and then spawn the number of threads again for the inner loop. So you can quickly end up with a lot of threads, maybe more than you actually intended. Your system can actually handle. You might have to be a little bit more conservative about how many threads you're spawning for the outer loop, so that when you're spawning additional threads for that inner loop, you end up with more threads than you actually get. So just be aware of that if that's something that you're trying to do. If I were doing this, I would probably start by just parallelizing one of these two things, not both. I would probably start by parallelizing blocks. If I were being honest. So I'm going to write a Monte Carlo program. First, get it working for just one block, right? That shouldn't be too hard. Set random walks. Once you're satisfied that one walk is working, then crank your loop up to 10,000 walks and parallelize it. See how you're doing. And then once you've got that working for a single grid point, then see if you can start bringing additional grid points into it. But don't try to do all the grid points, as I've already said at least a couple times now. If you try and do the Monte Carlo over all the grid points, it will not compare performance-wise. You'll get the right answer, but performance-wise, it's not going to be a version. That's not what it's for. Pick a subset of the points in the middle. Get those to converge faster than the iterative version. Because the iterative version, I don't have the answer to any of these points until the whole thing is done. Right? Whereas the Monte Carlo, I can get an answer to one of these middle points without having to do 90% of these other ones or any of the other ones if I don't want to. That's kind of the advantage. So it lets me get these answers out without having to necessarily do the computations for all the points that I don't. Which makes sense, right? We can assume that, you know, these grid points are probably going to be pretty close to this temperature. So what's the point of even worrying about it so much? Any other questions can address? Great questions, by the way. All right. How many of you thinking about the Monte Carlo approach? Anybody actually thinking of taking a swing? Yeah? Got a couple takers, maybe? It's okay if you don't. You're allowed to change your mind. And if you get started on it and you're like, wow, this is way harder than I thought it was, it's okay. No harm, no foul. But yeah, if you are interested, please let me know how I can help you. Please let me know what questions you run into along the way. And I hope this is already somewhat clear by now, but in case it isn't, I'll say it again. I am not a super stickler on due dates. So just like the last homework assignment, if you need to take, you know, the weekend following to finish it up, especially if you're working on that Monte Carlo approach, I'm not going to complain at all if it takes you a few extra days to get right up into me. So don't worry about the dates. I don't want to say forever. Class ends eventually, right? But you can certainly have a little extra time on that particular. Even if you're not working on Monte Carlo, you can turn it in on the 20th, and I'm not going to be upset about that. So, that's all I have for you today. So unless there's any more questions, go ahead and call it a day. And I'll see you all back here on Wednesday. Thanks, everyone.